ನೋಡಿ ಓಕೆ ಅಂದ್ರೆ ಕಳಿಸ್ಬಿಡಿ. 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 ನೋಡಿ ಓಕೆ ಅಂದ್ರೆ ಕಳಿಸ್ಬಿಡಿ.
Good morning, Dr. Guru Prasad.
Yes, sir.
Okay, I was just checking whether
Yes, sir. Yes,
does
sir.
not
We are just
start.
starting now. Our HOD is just going to give the inaugural talk now. So just in a few minutes, just in a couple of minutes.
ನಾನಾ ಏನ್ ಹೇಳ್ಬೇಕು? ವೆಲ್ಕಮ್ ಹಲೋ ಮಾಡಿ ಮ್ಯೂಟ್ ಆಗಿದೆ ಮೈಕ್.
Uh, Very good morning to all of you for this faculty development program. I would like to now invite our head of the department, Dr. Puttappa sir, to give his inaugural talk for this faculty development program.
ಕೇಳಿಸ್ತಾ ಇದೆಯೇನಪ್ಪ? ಕೇಳಿಸ್ತಾ ಇದೆಯಾ? ಓಕೆ, ಸ್ಟಾರ್ಟ್.
Dr. Puttappa sir, we welcome you.
Yeah. Can we start? Guru Prasad?
Yes, sir. Yes, sir. Yes, sir,
Okay.
please.
Good morning to one and all. So on behalf of the Department of Civil Engineering, I extend a warm welcome to all the participants. And also I wish good morning to Dr. Ananth Ramaswamy, the Professor and Chairman, Department of Civil Engineering, Indian Institute of Science, who has accepted to give the keynote address to this faculty development program. Good morning, sir.
Good morning to you.
Thank you, sir. So now the faculty development program on civil engineering structures subjected to vibration. It is organized by the coordinators, Dr. Guru Prasad and GM Vaswanagowda, the faculty of our department. And of course, another one of our professor, Dr. Sridhar, is a person who coordinated with in making this faculty development program. And there are 6 sessions with various experts sharing their expertise. So I am very sure the participants will have a very good enriching experience for these 3 days over 6 sessions. So now as a head of the department, it's my duty. I cannot presume that all the participants will know about our institution, might have heard about it, but it's my duty to give a little introduction about my institution and my department. So our institution was started in 1962 by our founder chairman, Dr. M.S. Ramaiah, with 2 branches. And then today we have around 12 undergraduate programs in engineering, including one Bachelor of Architecture, and we have 12 Master of Technology programs in various branches, including a Master of Architecture in Department of Architecture, apart from the Master of Business Administration and Master of Computer Applications. And all our departments are recognized and accredited by the National Board of Accreditation. And our institution is also recognized and accredited by the NAC accreditation. Of course, for 5 years, and now this year we are going for a renewal of it, because of the crisis is going to happen. Next year, the renewal of that will happen. And all our departments are recognized as research centers by the University of Technical Education. And our department started in 1971 with an undergraduate program. In 1983, we started an MTech program in structural engineering. And our department research center is also recognized as a research center in 94 by the Bangalore University. Then we were affiliated to. Now, after the formation of the Technical University, our research center is recognized by the university. We have around 8 recognized guides, and there is 17 PhD degrees have been awarded, and 31 research scholars are pursuing the research in our research center, with one leading to the MSc in engineering, which is a 3-year course. So now I extend a warm welcome to all the participants to this faculty development program. So I wish all of you a good experience and a learning process which is going to happen. Now I request Mr. Guru Prasad to take over from here and conduct the program. Thank you very much.
Thank you, sir. I welcome all the participants to this faculty development program. And I would like to introduce Professor Ananth Ramaswamy, sir, the first speaker of the faculty development program for today. Professor Ananth Ramaswamy, sir, is also the chairman and professor in Department of Civil Engineering at Indian Institute of Science in Bangalore in the Department of Civil Engineering. He holds his bachelor degree from Department of Civil Engineering from Indian Institute of Technology, Chennai, and MS in Civil Structural Engineering from University of California, and a PhD in Civil Engineering from Louisiana State University. And a brief summary of his research interests are in the area of material characterization, condition assessment, health monitoring of structural elements, namely concrete, steel, and composites under monotonic and cyclic loading, along with thermomechanical loading, structural protection methods, adopting FRP and cementitious composites, and the use of structural control composites and smart material technologies. He has been recipient of various awards such as CPWD Medal of Indian Roads Congress for Best Paper on Maintenance, Best Reviewer Award from Journal of Bridge, Best Reviewer Award, Journal of Bridge Engineering, American Society of Civil Engineers, Best Reviewer Award, Journal of Materials in Civil Engineering, ACE. He's also been the editorial board member of several refereed journals, such as he has been the associate editor of Journal of Structural Engineering, American Society of Civil Engineers, associate editor of Journal of Bridge Engineering, American Society of Civil Engineers, and associate editor of Sadhana, that is an Academy of Engineering Science, Indian Academy of Engineering Science, Springer. He has more than 26 years of teaching and research experience. He has guided 10 PhD students, 8 MSc students, and 38 ME students. Along with that, he has 60 plus international journal papers, 52 international conference papers, 21 national conference papers. He has 13 sponsored projects and 40 industrial consultancy projects. He has also been member of different, he has been in the membership in evaluation and different assessment committees, such as he has been the member project assessment committee in the area of civil and environmental engineering of the Science and Engineering Research Board, that is in the Department of Science and Technology, DST, Government of India. He has been member of project assessment committee, early career research and postdoctoral fellowship also, and few more committees he has been a member of. So we give you a warm welcome for this talk to for our faculty development program, and we thank you for giving us your talk for today. Thank you.
Thank you, Professor Guru Prasad. I will now share my screen, and I hope you are able to see it.
Yes, sir.
Is my screen visible?
Yes, sir. Yes.
Okay. Good morning to all of you, and I thank Dr. Guru Prasad and MSRIT for giving me this opportunity to speak to all of you. And thank you for the rather long introduction, but I would have preferred a much shorter one. My email ID is here on the first screen. You may contact me whenever you wish. So with this, I will go into my presentation, which is focusing on repair and retrofit of concrete structures. This is something that is important in this day and age where you have aging infrastructure is an issue. So briefly, the overview of my presentation will focus first on how you assess the condition of a system, of a structure, because repair requires an understanding of what the structure is today and what caused whatever perceived damage and extent of damage before you can prescribe a repair. So there are many ways of doing this. One approach is to do some loading, and that is what I will illustrate. And then there are possibilities of non-destructive testing like rebound hammer, Pandit, etc. So the first part of my presentation will look at some of these, and in the example that I present to you is from bridges, where some of us, my colleagues and I, were involved, for example, in Indian Railways projects where we were looking at the condition of bridges. Now, after that, I will get into some fundamental issues of seismic loading. Since this is a vibration conference, I thought that would be of importance. So before we get into retrofitting, again, it is important to understand how seismic loads affect a structure. So in that context, looking at structural forms, symmetry in plan and elevation, advantages of simple clear forms so that one understands how loads get distributed to various elements of the structure is an important step. Thereafter, I will also touch upon ductility, which is the basis for designing systems where loads may be rather high, and it's quite unattractive to be trying to design something to remain elastic all the way. So given that context, we will look at ductility before I get into some of the ways in which damage can be assessed and evaluated, and thereafter decide on repair and rehabilitation strategies. A retrofit is something you do when you want to look at enhancing it beyond what the system could take in its original way. So therefore, retrofit is also something that one can do. Finally, I will show you an example or two to get across the points involved in the repair scenario. So without any further ado, I will get into the presentation. I may have loaded too many slides in this, so I may along the way skip a few slides which I don't think make a point at this, given the limitations on time. Okay, so to start with, the slide I'm showing you here is the Dudhsagar waterfalls, which people in Karnataka would be quite familiar with. This is actually a bridge across by the Indian Railways, and we were looking at condition assessment because they were interested in enhancing the load. So they had various ways of conducting tests, and our objective was to look at, can this bridge, which was built in the 1870s, take an higher load, axle load, than what it currently is rated for. So in that context, we conducted a series of tests, and we had instrumented the bridge with strain gauges, LVDT, accelerometers, etc., tilt meter, temperatures, and we did a whole lot of static and dynamic studies on that, and some NDT acoustic emission studies as well. Core samples could not be taken given that the bridge is a live bridge and is open to passenger and goods traffic. So any intervention was not admitted, and we had to work within the operational loads that we were allowed to put on the bridge. And since this is a very old bridge, there are no drawings or design details. So we had to reconstruct our understanding of this bridge based on measurements and modeling, and try to reconcile these two to get a current condition assessment, and thereafter decide whether it can take a higher load. So in that context, we also did some finite element modeling and tried reconciling measured results with computed results, based on which we had, by suitably adjusting the material properties, the boundary conditions, etc., we were able to show how this system performed under the loads at which the field measurements were taken, and thereafter used the same model for enhanced loads to show that the system remained elastic in these revised domain. So obviously, the question of repair retrofit would come in if your system exhibited some kind of damage in the model, if you went beyond the rated value, and or rather for the rated value, you saw some kind of inelasticity evolve into the system. These are some of the other bridges that formed a part of this study. The truss bridge is outside the Hospet station. We did, you can see, in fact, the LVDT was mounted as a standalone because this is a bridge across one of the water canals. And you can see that our model and measured results kind of tally in the way this model was reconstructed. This is a steel bridge that you are seeing here. Similar things were also done at Toranagalu, another bridge just outside where the Hospet Bellary region, which is primarily for carrying iron ore traffic. This is another such bridge in that system. It's a viaduct, and given that the drop is something like 40 meters, clearly LVDT was infeasible in this case. And what we eventually did was mount strain gauges at various depths, at various cross sections, and used moment curvature ideas in order to estimate the deflection from measurements, and thereafter reconcile it with computational model information in order to take this process forward. This is one more bridge like that in Gadag, where the material is brick masonry as opposed to stone masonry in Dudhsagar. So the point I'm trying to make is that condition assessment is one approach to look at the system as it stands today. Adequate measurements need to be taken in order to be able to reconcile model and measurements and get a handle on the problem. Thereafter, you can look at whether it can take enhanced loads and so on. Okay, so now I move forward and talk about seismic loads. So very often we have structures which get damaged, and we wonder how is it we designed something and it still experienced damage. So in that context, it is one of the issues is we may not have instrumented the system, so we don't really know what is the kind of accelerations the structure experienced, and therefore you need to reconstruct as a post-event some contours of PGA to understand what was the structure actually exposed to. Another approach is a co-event process, where you may actually have seismographs and vibration monitoring processes. And yet another approach is pre-event. you instrument it and construct damage probability matrices, fragility, and based on that evolve your design process. So there are three different ways of attacking such problems. Obviously, if you instrument it, you have an idea, but until the event happens, you don't have data. So all of this requires some idea of the likely risk and the relative importance of the structure based on which you design new systems. Now, given that systems or structures already exist, you may want to again evaluate and see whether any intervention is needed. And in that context, repair retrofit becomes an important question. So going forward, some ideas on what is earthquake. I guess many of you know that these are some slip dip events in the deep under the ground, which translates into vibration waves, and you have different nature of vibrations depending on the soil, the bedrock, and the proximity of the structure vis-a-vis the hypocenter. So correspondingly, you will see that the signatures of acceleration, velocity, and displacement differ considerably when you look at something as near field, which is like 20-25 kilometers from the hypocenter, something much further and very far away. So duration and pulse. Near field have strong pulses but short duration. Far field seem to have longer duration with shorter excitation amplitudes. So correspondingly, there are differences in the kind of amplitudes and frequency content that are present in the seismic signature, and which you have to accommodate in your structural analysis. Moving forward, they are also dependent on the nature of the structure, the soil conditions, soil amplification, and interstory drift, etc., etc. And over a period of time. Hello, can I continue?
Yes, sir.
Okay, so there are differences in the nature of design that wherein you take, for example, just the fundamental mode, or higher order modes may also become significant, and therefore you accommodate. So you can see that higher ductility demand due to pulse action is an issue for near field system, and of course if you make something much stronger, then the available ductility reduces. Then the other thing that you can't design for the worst earthquake, then you are putting in a lot of money. So you really have to look at frequency of events and rare events. So you can see frequent, occasional, rare, very rare, and associated with that, the magnitude of the acceleration or the peak ground acceleration that you have to consider is different. So therefore, if you are designing something for 50 years and assume that you would design the system to be operational and occupant safe for frequent earthquakes, which are of the order of 0.02 G, and you would expect the structure remains collapse free for very rare events of 0.3, 0.4. I mean, if you really need to go that high, it depends on the importance of the structure. The other thing that you have to remember is that there is a way in which you can relate magnitude and recurrence relationship. That means, given the kind of magnitude, what is the likelihood of an event of that order occurring over a period of time, the recurrence window. So that is something that has been statistically studied, and you have the Gutenberg-Richter relationship that I show here in a log form. Similarly, there is something called attenuation. That means with distance, the magnitude reduces, and that has to do with soil parameters and distance of the epicenter, the kind of bedrock over which the structure is, how much of overlay exists, etc., etc. So one can evolve an attenuation relationship and use that in the context of a particular site. So given all of these parameters, the way in which seismic analysis is conducted changed over a period of time, from one where we put a point load at the top to one where a distributed load was considered, to concepts of response spectra and yielding, etc., which I guess Professor Raghu Prasad will be talking about later today. Now, in the context of ductility, which is an important parameter in design, you have ductility is a quantity that you can establish at different levels. For example, at a cross section, you talk about material ductility. And then when you go to member, you talk of member rotation and rotational ductility. And eventually at structure, you are talking about structural ductility, which is in terms of displacement. So codes will tell you a certain magnitude is associated with a certain ductility at the structure level. But in order to arrive at that, your design has to look at components, members, and therefore member ductility at joints and curvature ductility at cross section are important components that you have to accommodate in order to be able to achieve your target structural ductility. So the whole process is kind of forward and backward integrated. And of course, you have to account for a global scale, which is at macro, to local scale, which is at micro, to specific site conditions as well, which account for soil strata, presence of soft soil, enhancements in ductility demand, etc. So the philosophy of seismic performance levels are, as prescribed in some of the international codes, are shown here. And in that context, you can see you have operational, fully operational, you have immediate occupancy after an event, you have life safety, and finally collapse prevention. These are the four metrics going in the horizontals. Associated with the horizontals, you have overall questions like no damage, light damage, significant non-structural damage, and possible structural damage, which means collapse prevention is about all that you can realize going down the vertical of overall. In the same spirit, you look at the last column, you are talking about repairs. When you say operational, it means no repair is needed. When you say immediate occupancy, some minor repairs may be needed. When you say life safety, then you are basically repairing non-structural elements plus immediate repair of some structural components. And when you talk about repair in the context of collapse prevention, you are really asking whether it is worth repairing or whether you should demolish it. So these are levels at which you have to understand when prescribing a medicine becomes important or you are beyond hope. So in that process, you have to look at changes in concept that have taken place over a period of time. Original traditional designs had only a single level where you looked at selected performance, site suitability, conceptual design, to a more progressive approach where you look at rigidity, strength, ductility as three corners of your design triangle, and you try to get the best bang for the buck. So in the same way, you have ideas of preliminary design where you look at certain things, and then you come about final design, and eventually you do the final detailing in order to enhance the required ductility at certain critical sections. So in the same spirit, construction practices have also gone through some changes in terms of quality assurance, in terms of monitoring, in terms of refurbishing or repair retrofit. So rules for this are slowly evolving. In the earlier times, there was no rules and people just went about repairing without having a clear idea of how things should be done. Whereas now we have more tools in our hands and therefore a more informed judgment is feasible. So then you talk about verification of performance. So performance, as I mentioned to you, is if you go look at the verticals, you have rigidity, strength, and ductility. And along the horizontals, you have serviceability, damageability, and survivability. So in the context of survivability, strength and ductility are the key parameters, wherein in the context of serviceability, rigidity and strength are the important parameters. Damageability is somewhere in between, where you have to look at all of these three parameters together. So in the big picture, you can see how a structure is going to behave, the initial elastic, then the elastoplastic, then some kinematic rotational, and then eventually a collapse where you are allowing the system to slowly dismantle itself. So in that context, it is important that damage assessment is something that you do. So damage assessment requires an understanding of the load to which you are trying to build things, where you don't have seismic excitation information. You have to construct using post-event processes, something like the Mercalli intensity values or PGA contours, which will give you, based on field assessments of a large region, contours of PGA that you need to consider while replacing a structure in that, or replacing or repair retrofitting a structure in the given contour. So it is a process by which you get an idea of the likely loads, the recurrence, and the conditions that the structure has previously experienced, and based on that, the level of damage that may have already been accumulated into the structure. So knowing the patient is an important process before you can prescribe the repair. So one yardstick that is often used is the Park-Ang model, which is something that evolved in the 1980s. Of course, in recent years, many new measures are there. I won't get into those details, but you can see that the yardstick ranges from none or no damage to minor, moderate, severe, and eventually collapse. So these damage indices help you decide the extent at which you need to start looking at repair retrofits. So they consider flexural and shear cracks, steel yield, bond degradation, crushing of concrete. In the case of steel structures, it may be local buckling, flange web, bolt yielding, weld fracture, etc. So local indices can then be built around these, and global indices at structural level need to accommodate some of these local. So there is a forward integration from local to global, and one needs to look at, for example, this particular integral that tells you the damage index that you develop from this kind of accumulation process. So damage less than 0.1 means no damage, and values of 1 or more basically imply collapse. So you are looking at a graded damage range, 0.25 for moderate, 0.4 and above for severe. So you have associated with this a damage probability matrix, which can tell you associated with it the damage index and the likelihood that you are seeing. For example, an index 6 would indicate most structures would be in the range of minor, whereas as you go forward, damage level 10 would mean 90% of these structures in that neighborhood have a 90% damage. That's when you look at moderate damage. That's when you look at something at 10. And obviously 12 would mean that moderate is something that is common, and you may even have a severe instance or a near collapse condition wherein it doesn't become important to even talk about damage anymore. So based on such indices, one can construct what are known as vulnerability or fragility curves. So these tell you basically the risk that you are having to look at, and your investment will naturally correspond to the risk you are able to accept. So if you are accepting high risk, you will invest less. If your appetite for risk is rather low, you will invest more and try to meet a higher target of safety by putting in more intervention. So these are the ideas that you need to carry forward. And of course, you can look at sensitivity of parameters, 5%, 10% variation around the mean value, to construct fragility and windows within which you are likely to play around with the parameters, and then based on that arrive at the kind of risk or PGA that you need to consider for the frequency of a certain event, and thereafter invest on your appetite for risk. This is just to illustrate how a joint can experience considerable damage, and thereafter, if it is very severe, the repairability issue becomes much more complicated. So this is an illustration of repair of a reinforced concrete joint using pre-stressing, that is to kind of confine the joint. Another approach, of course, is spiral reinforcing and taking your rebars across and so on. These are just to illustrate something along the way. I will get into more details as we move forward. So seismic design philosophy revolves around, as I mentioned earlier, serviceability, ultimate limit state, collapse. So given these different measures, you are identifying a PGA, the likelihood of a return of a certain event at a certain PGA, and therefore your structure needs to withstand accordingly. Ground excitations with levels of, there is a philosophical difference in old codes and new codes. Modern codes require no collapse, and the criteria is structural system should meet applicable code provisions on serviceability and ultimate limit stage. A damage limit stage, where structural forms, foundation, design should conform to design seismic action. And factors influencing structural form, this is something I will touch on a little bit. We'll look at issues like simplicity and symmetry, length in plan, shape in elevation, uniformity and continuity, stiffness, failure modes, foundation condition. The reason I bring this up is that repair retrofit doesn't simply mean damage repair to existing members. One could also improve the structural form by introducing new members as a concept to bring about simplicity in the way the forces get redistributed, and therefore you are mitigating the risk on certain members that were previously getting damaged. So repair retrofit is a concept that goes beyond repairing a certain member and looks at the structure in its entirety and sees how we can alter the load distribution in the structure so that its performance improves when a future event occurs. So intervention can also mean introduction of new members rather than simply fixing an existing damaged member. It would of course mean fixing a damaged member, but it would also mean that introducing new members would reduce the load share on these previously damaged members subsequent to repair. So to illustrate that point, you can look at these rectangular forms, which primarily tell you that there is a certain symmetry in the plan, which could be through an arrangement of columns and beams. It could be through an arrangement of shear walls. It could be through an arrangement of frames and shear cores or stiff shear wall cores in the center as shown here. So similarly, building should be regular and planned. You should not have re-entrant or discontinuities, irregularities in shape. Shear walls should span full distance between adjacent floors. You can't have half depth or floating walls, etc. All elements forming the structure, including foundation, should be interconnected so that they redistribute across. Short columns, because of mezzanines or stiff masonry walls below windows, should be avoided because they attract larger force than you actually anticipate and therefore could get damaged. Flat slab systems without any beam should be avoided where seismic risk is high because these are brittle elements. Okay, large openings in infill systems should be avoided. Weak points in the slab endangering its diaphragm action should be avoided. Structure should have strong column and weak beam because you really want hinge formation in the beam, not in the column. So preferred hinge formations are not in the column, not in the joint, but in the beam. Then similarly, structure should preferably have a second line of defense. That means basically you want redundancy built into the system so that there is multiple paths for load transfer without causing serious damage to the structure. Then construction site and foundation soil should be free of risk of soil rupture, slope instability, settlements, liquefaction, etc. All footings should be at the same level, and only one type of foundation should be used. You don't want differences in foundation. Footing should be interconnected where possible with a mat or by a grid beam, so that you are in a sense building about a certain redistribution across the entire closed frame. Now I go back to both favorable and unfavorable structural forms. You can see on the left side two figures which show you undesirable angles or C shapes or head shapes, as opposed to more favorable arrangements wherein you introduce some hinges, discontinuities, etc., so that the structure performs much better even if it is shaped more or less in the same way. Expansion joints where you need to give as opposed to keeping it continuous. Similarly, on the lower part, you can see how presence of shear walls go about bringing a certain symmetry in form, and certain eccentricities between the stiffness and inertia center are avoided. The left side shows you that there are eccentricities and therefore torsion can be induced, whereas in the right hand you are seeing that there is coincidence of mass and stiffness center or alignment of mass and stiffness center that prevents the possibility of torsional moments being excited. Similarly, there is an issue in terms of elevation also. Just as I showed you for plan, you also have similar questions for elevation where you want a certain symmetry or favorable alignment of systems so that you have a better understanding and design possibility, having more confidence in how the load will get transferred. So uneven depths are shown to you on the left side as opposed to even depths or modification in the arrangement, so as preferred or favorable force transfer takes place in excited systems. This is another illustration of the same concept. You don't want half walls which build in unexpected levels of stiffness over intermediate depths, which are quite unfavorable to overall performance. So the other issue is comparison of merit of stiff and flexible structures. Flexible structures are especially suitable for short period sites. That means where you are looking at seismic excitations which are short in time period or in terms of frequency content, then you want flexible structures. Whereas having a stiff structure there would attract much higher forces and could be a risk. Similarly, flexible structures will have higher response on long period sites, and therefore this is not something that is desirable. You would have to therefore introduce shear walls, bracings, etc., or base isolation and other absorber concepts in order to be able to design in. So therefore, a bottom line is understanding of soil, understanding of the frequency content of seismic excitations, and the fundamental period of the structure are all important in trying to evolve the best system for the given site and structural demand. So stiff structures are suitable in long period. These are exactly the other way around, and stiff structures for higher response to short period sites. So appropriate ductility, not easy to achieve. So these are not something that you want. You have to therefore have a good understanding and be the driver in control of your design process. So failure mode control, you need a good design practice demands keeping the probability of failure low by designing for minimum required strength, but also ensuring that undesired failure modes are less likely to happen than others. So when loads are going to be in exceedance, you want to be sure they follow a prescribed path that you have an understanding over, and therefore you introduce desirable hinges in those elements which you can go back and intervene on at a later date, and thereby address questions of safety against collapse, safety against serviceability, and possibly operationally safe. It is all a function of the investment that you are likely to be making. So here I am showing you different failures that can happen in columns where concrete spalls, the rebars buckle or hinges form, etc., etc. And you can have explosive spalling and related brittle collapse, as I showed you in the bottom of the screen. Similarly, you have damages in walls, shear walls. So the possibilities are numerous. The challenges, therefore, are in having a good understanding and providing the required design in the first place, or if not at that stage, providing the right intervention at a later date. So similar scenarios are also there for walls, where you are looking at seismic excitation, the possibility of certain critical paths, local crushing, and you can see on the right side, these plots show you a certain necking taking place near the origin, which suggests that there is considerable bond slip between the reinforcement and concrete, and therefore you are seeing the pinching. If you have nice big load deformation closed loops, you are dissipating much more of energy, which is a good thing. But when you start seeing progressive pinching, that basically means you are having a lot more of damage taking place there without dissipation of energy. So that is not necessarily a good thing. Similar things are also seen here: flexural cracks in beams, bending shear, shear failure at an indirect support, flexural failure at lower faces. These are all illustration of the kind of failures that you can get, and not all are easy to intervene into at a later date. So shear failure in shear wall and coupled beams. So that means you have a frame and you have a shear wall and you have a coupling element in between. So these are not something that are easy to design. You must have a fairly good understanding of how forces will transfer through the coupled beam, so that you can design it and detail it properly. So here I'm showing you an illustration of joint failures, where spalling of the core, beam yielding, column rebar yielding, anchorage failure, which can be very brittle, shear failure in the core, which can also be very brittle. So these all lead you to more difficulties when you come back to intervene. Similarly, punching, that's a very brittle process and the whole slab will collapse. Similarly, the wall panel with huge damages would mean that the panel can simply fall off in the infill. So, structural forms for seismic resistance, you are looking at moment resisting frames. They avoid potentially brittle failure, but they tend to sway excessively. Framed tube structures compromise between pure moment resisting and shear structures. These have less side sway and reduced ductility. So you are always having a plus and a minus. So arriving at the right mix is the challenge that you as a designer would always face, whether you are designing a new system or whether you're visiting a dam system and trying to provide the required intervention. Again, looking at concentrically braced frames, center lines of members, intersect members, meter and brace frame, better than resisting frames in terms of sway deflection, but are inclined to buckle. So these are basically compression struts or tension struts. Used in construction of towers, trusses and frames, they are not as good in seismic resistance when members are in tension only, having permanent deflection. Okay, so hybrid systems, they need great care in design. You may think there is some clever, you may think that it's clever to do hybrid systems, but without a good understanding, hybrid systems can be a pitfall. Energy isolation and dissipating devices is another way of providing intervention. Repair retrofit doesn't mean necessarily just going and repairing damaged members. You may have to do a little bit of that, but to isolate a system at the foundation level, not easy, but this can also lead you to an improved way of reducing risk on the structure going forward. Another possibility is adding an absorber system at the roof. For example, water tanks have been designed to provide required level of sacrificial element by way of attracting vibration and protecting the primary structure. So you have both isolation and you have absorber. Both of these concepts can be used as a suitable intervention. So this, for example, the lower part shows you what an isolation is. It is basically like elastomeric bearings or lead exclusion bearings, or even a semi-active system with springs and dampers that can be introduced between the column and the foundation so as to isolate and prevent transfer of too much of seismic energy into the structure. So these are all possibilities in the process. I now move forward to the next element, which is ductility, looking at material, sectional and structural ductility and seismic sustenance. I understand the next speaker will talk about it in more detail. I will only touch upon it briefly to give you a flavor of how all of these integrate in to create the big picture, very much like a jigsaw puzzle. Okay, so seismic resistant design and governing design principles. So seismic energy dissipation should take place in elements which possess adequate ductility and are easy to repair. So beam yielding is preferred in buildings, but in the case of bridges, you don't want a pier yielding, or rather pier yielding is preferred in buildings, not beams. So you are seeing that weak beam, strong column is something that is desired in buildings, but when it comes to bridges, it is easier to go back and intervene into the pier, that is the column system. So there is a functional aspect to the desired design. Seismic energy dissipation should take place through flexure yielding mechanisms and not through brittle, shear, bond slip or anchorage failure. So whenever you have slow ductile yielding, you are always providing adequate warning to occupants, and brittle mechanisms are sudden and offer little or no warning and are a bigger risk in terms of the life safety aspect. So when you go forward in terms of designing, joints, common areas of adjacent elements should not fail before the member attains the full strength. So joints, you don't want hinging. Reinforcement provided in RC section should ensure ductility and should not hinder construction. You can't put so much steel that you can't construct. So the right balance is something that you have to keep in mind. Structural elements which for design purpose are not considered as part of seismic action resisting systems should be in a position to maintain their own load. That means partition walls and things like that must be able to carry their own load and not become a nuisance in the overall scheme of things. So there are multi-level criteria that you have to consider in your whole process. Design seismic inputs, a global scale, local scale, required versus availability of ductility. So ductility demand versus ductility provided. So now when you talk about seismic evaluation, you are looking at 3 different return periods: 20 years, 475 years, 970 years. Obviously, normal buildings you may do for 20 to 50 years. Something of more importance you may do for 470 years. Something of very critical importance like a nuclear power plant, you may even look at 970 years. So correspondingly, the amplitude that you consider as a PGA would differ. Associated return periods may be much longer, but nonetheless you would want to design it that way in the context of a seismic event hitting a nuclear power plant as opposed to a building. So your appetite for risk is always under investigation. Okay, so here I show you a design spectra and associated with it 3 different yardsticks. One is serviceability, another is damageability, and the third is ultimate limit states. So you are looking at different things and associated with it different base shears that you are looking for. So for example, you may design for PGA and a smaller base shear that may be required at a shorter period of return period, whereas if you look at not return period, I should say fundamental period, sorry. And when you talk about ultimate limit states, you are looking at something quite different, and therefore you want that to be over a different range of time periods, the level of safety, ultimate limit. So you have therefore different envelopes that you are seeing here. One for serviceability, which goes up to a maximum of 3.25, The second one at a damageability, which goes to a maximum of 2.5, and the one at ultimate, which goes to a value of only 1. But obviously the associated forces are much higher. So you design for a higher force, but you are saying that it remains safe for that higher force. But when you talk about lower force, you want it to remain safe over certain periods. So this is something that you will get a better understanding when you start looking at response spectra based design. This kind of plot with different metrics will be something that you revisit later today. So global analysis, you are looking at seismic shear distribution over structure height, serviceability limit states, damage limit states, and ultimate limit states. So global analysis looks at preliminary design, bad choices of configuration leading to poor design need to be eliminated. Then you progressively arrive at improved designs. So your final system for a building would be one that is conforming to weak beam, strong column with a good plastic hinge rotation and capacities, moment curvature relationships at those points, so that adequate redistribution and desired collapse mechanisms evolve. So all of this would require some corrections when you talk of pulse load and high velocity component, etc. So going forward to local analysis, you are looking at cross sections and members, and therefore associated rotational capacity or curvature capacity at those sections must be such that you can perform more at the local level in order to be able to accommodate the desired structural performance using the global metrics. So there is a connectivity between local and global yardsticks that need to be addressed properly. So I will briefly go through what is known as a pushover analysis. Pushover analysis basically looks at treating the seismic load as a static force and trying to see how progressive hinge formations take place, and from there identify whether your detailing is adequate to accommodate proper redistribution taking place in the system. So obviously ductility becomes an important yardstick in this process, both at structural, which is displacement ductility, local, which is at member, and curvature, which is at cross-sectional levels. So there is a forward and backward integration process that must be accommodated for in understanding ductility as a basis for design. So you look at member, joints, columns, connections, etc. Make corrections for strain rate related issues, make corrections for hinge formations, etc. So plastic hinge formation is also something that you want in a certain way. And of course, bond degradation and associated sliding of reinforcement reduces the amount of energy dissipation at a section. So therefore, ductility is something you want in a certain way. You don't want pinching action, but if it does happen, then basically you are allowing for a reduced energy absorption. Again, here you are seeing benefits of looking at stress strain in a material and advantages of going for high performance, not high performance, high strength concrete, better confining approaches, etc., and related stress strain response. The top line you are seeing sigma c equals fc into 1 minus z into some quantity. Z is basically the post peak component, which tells you gives you an idea of how confinement provides you advantages in overall stress strain response. These are some things that you may be quite familiar with: the cross-sectional analysis, looking at phi y, which is the curvature at yield, and phi u, which is the curvature at collapse. So these two are quantities that you make use of in arriving at cross-sectional ductility, which is given in terms of phi u, which is a measure in terms of epsilon u and epsilon c and epsilon y. So this yardstick will differ when you go to doubly reinforced sections. There are differences in the influence that higher reinforcement brings with it, a reduction in curvature, influence of axial load on the curvature. All of these have interesting interrelationships. So ductility as such decreases with increasing tension steel, increases with increase in compression steel, reduces with increase in yield stress. Variations of curvature ductility for single and doubly reinforced confined sections are shown, and you can see how these contours change. Effect of confinement is illustrated to you here, and obviously more confined concrete leads to a more gradual reduction in the stress beyond the peak. Curvature ductility ratios for column with confined and unconfined section show you how these parameters change. Curvature ductility ratio for confined column is shown on the right side. So similarly, effect of cyclic loading, you can see how the envelope remains the same, but the unloading reloading process have some differences. Again, confining also changes the peak scenario in terms of the failure surface. You can see differences in your overall performance that you can see. So concrete under multi-axial stress and an understanding of that is an important issue when you provide the detailing. So high confinement leads to much higher strength. As you can see here, uniaxial versus biaxial, there is a 20% increase. And of course, when you go to triaxial, there is an even further increase. So all of these can then get into models, and appropriate properties for the Young's modulus, strength, etc. need to be introduced into your model in order to predict the overall response. I show you a few more plots here of differences in stress strain response under biaxial cycling, equivalent uniaxial stress strain given the multi-axial stress state that may be present, and the advantages of triaxial compression and the failure surface. You can see, of course, on the right side that with triaxial compression, the failure surface expands in space. That means I am creating a much larger failure surface and delaying failure by having better confinement. And you can see also changes in stress strain response with increased confinement, how things change. So parameters affecting confinement are ratio of transverse steel, yield strength, concrete compressive strength, spacing of hoops, hoop pattern, longitudinal steel, rate of loading, strain gradients. And this is something that will take you back to your first year when you talk about hoop stress. One loop around the concrete tells you what kind of pressure can be introduced by that hoop. So more hoops, better confinement, and further enhancements. So all of these are again illustrated to you in these plots. I will quickly move forward. Requirements of steel bar for seismic performance. Steel in should not fracture, should be sufficiently large so that ductility is assured. Yield stress of steel should not be significantly higher, as this would allow shear forces to build up. So obviously you make something strong in one direction, you are making it weak somewhere else. So it is important that you have an overall understanding of the scenario and introduce your interventions carefully. This is an illustration of a bond slip and how bond behavior is an important parameter in your design and repair. So factors influencing bond under cyclic load: concrete compressive strength, cover, bar dia, geometry of bar, yield value, position of transverse steel, casting position, vibration, revibration, stress or stress range, temperature, surface condition, etc. Effect of lateral pressure, of course, confining means higher strength and improved bond. Bond also improves, as you can see in the plot below. So this plot gives you a bond stress slip curves and of course the pinching action, which is not really a desired component. So there are models that tell you how bond slip can be modeled and introduced in computational models, such as the CEB model for bond stress slip. It basically tells you how the bond shear at the interface responds and how you can introduce it into your computational model. So I am showing you here something connected with moment transfer by bolts, side connected weld and links, and in the context of pre-stressed sections, adequate ductility can be realized with controlling the depth of the compression block, use of multiple tendons. So everything has some role to play, whether you are looking at concrete, whether you are looking at pre-stressed concrete, whether you are looking at structural steel. Lack of adequate lateral restraint can lead to instability, strains in hinge growth till initiation of cracking, which grows rapidly into a fracture. You can always have joint fracture, weld breaking, buckling. So there are so many different modes. You really don't have a clear idea what is playing an important role in the failure mechanism. The rate of loading enhances yield stress. Different connections result in changes in damping, 2% for weld, 7% for bolting, etc. Rotational capacity at hinges, these are expressions that you can find in the literature. I will skip some of this. Ductility in steel, cyclic load at low strains are quite stable. Hysteretic degradation in web buckling, flange buckling, lateral torsional buckling, all of these are possible, and you need to provide adequate stiffeners in structural steel sections to prevent certain forms of local failure. This is a larger picture of a frame and different ways in which the hinge formation can evolve. So I will skip some of this and move to the thrust of today's presentation only now, which is related to the idea of seismic resistance repair, available seismic resistance, residual seismic resistance, and the loss that has taken place that you are making up through the process of repair. This plot really shows you differences that you are seeing in terms of required versus available. So it has to do with the ductility class that you are designing for: low ductility, moderate ductility, high ductility, etc. And you can see here yardsticks VB, VC, VD, and associated with that repair and strengthening. Repair means bringing it back to original design. Strengthening is taking it beyond original design. That is when you call it strengthening and retrofit. So possible reasons for inadequacy: well, design provisions have not been fully implemented, some poor design, structural design built for different bases of design codes have changed, building usage, functional usage of the building has been changed, environmental effects have led to corrosion, spalling, etc. So there is degradation which you are trying to fix. So repair rehabilitation has to do with damaged structure or non-structural member repair, reach minimum strength, stiffness, ductility that they had before the earthquake. Strengthening or retrofit means going beyond the original design to a enhanced target that you are trying to seek. So there are different ways in which these quantities can be measured. I will skip some of this and move forward. So you can really look at what is the dosage of medicine and where you want to introduce it. Again, I revisit some of these structural forms. On the left side, you can see certain unclear forms, which through an intervention process, you can make into a better arrangement and thereby reduce risk on certain members. So unclear forms can be converted into an acceptable arrangement by way of a repair process. So repair doesn't mean only fixing damaged elements. It can be also introduction of new elements to mitigate and reduce loads on other elements in a more understood manner. These are similar concepts that are shown to you here: action inside an RC frame, addition of a truss system inside an RC frame, improvement of stiffnesses, eccentricities with additional walls, additional of a wall inside. So these are all intervention measures that improve clarity in the force transfer mechanism, and therefore meeting required performance levels in a meaningful way. So ductility of a structure, of course, you want strong beam, weak column for frames, adequate shear reinforcement, you don't want shear failure, confined compression zone so that you get good hinging mechanisms. Again, decision on degree and level of intervention, type 1, 2, 3, 4, this is like dosage of medicine, improvement of ductility and energy dissipation mechanism through upgrading of existing structural systems, increase of strength and stiffness through strengthening. Type 3 is increase of strength, stiffness and ductility through strengthening. Type 4 is increasing strength, stiffness, ductility through addition of new elements. So the last one is where you are looking at adding new elements by way of intervention. So this is how you can address the overall ductility question. So again, you are rating the building based on layout and strength index. In terms of structural layout, good, acceptable, unclear. Strength index required, you are seeing on the horizontals. So A, B, C, D, E are rating values which tell you what is the level to which things are good or poor. Based on the following expression, you can also arrive at the base shear for reanalysis and design under strengthening. That means post-strengthening, how you handle the system. Degree and type of intervention, you can again, these are categories A, B, C, D, E, which came up in the previous slide, and required versus available is shown to you, and therefore you have a way of moving from the left vertical to the right vertical in terms of repair, strengthening, feasible, unfeasible, etc. So same thing in terms of unsatisfactory ductility. Previous one is where ductility was adequate and you are intervening. Here ductility is inadequate and you are still intervening. And eventually you are looking at subjectivity of the intervention. So therefore modeling of the structural system for determining VC, classification of the layout, choice of the type of strengthening are all questions that you are trying to address. So structural assessment is something that you start from the drawings where drawings are available, information on design implementation at site if it's available, check on material quality, details of damage zones, check on original analysis if available. Structural adequacy check is then based on such a survey, and then based on understanding you arrive at the final decision on repair and strengthening. So information on strengthening can look at estimates of dimension, estimation modified stiffness, estimation of behavior factors in relation to local versus global ductility. So these are some of the other issues when you talk about redesign of strengthening through reanalysis. So again, you are looking at after strengthening what is the current capacity and then deciding whether this is adequate. So there are other issues that you can look at: selection of behavior of materials, selection of partial safety factor, calculation of design resistance, verification of safety. All of these are issues that you do going forward. So general issues of intervention, of course, you start with cost. No money, no intervention. Durability of original versus new elements, availability of skilled workmanship, equipment, materials, quality control, aesthetics. You don't want intervention to make the system ugly. Occupancy impact during and after work. How much do you have to empty the building? Can people continue living there or working there while you intervene, etc. are question mark. Preservation of architectural identity is an important thing when buildings have some historical value. Technical aspects, you are trying to make irregular systems regular. Strengthening looks at codes fulfilled after intervention or not. Non-structural elements should be strengthened if low damageability of the element is not satisfied. Enhanced low ductility is required in critical areas. Spread areas of potential inelastic behavior as much as possible. Repair and strengthening, depending on level of desired resistance and damage, you want to intervene with the kind of mechanisms that are available to you for strengthening. Ductility improvement through confinement is another possibility. So as such, the entire scenario looks at several different issues starting with an understanding of the structure, the understanding of the load, the possible different mechanisms through which repair can be introduced, what it does to ductility post repair, etc. must be understood before you select the most appropriate repair. I illustrate to you some functional ways in which repair is being done or could be done: shoring and then repairing, release the load, repair and then reintroduce the load. Formworks of different kinds that are used, repairing with timber grillages, tying of column with steel profiles, bracing or buttressing, then bracing with diagonal struts between the columns, not with infills but with struts, repairing joints where you have to injection grouting, strengthening with metallic sheets, welding with reinforcement, new bars. Column repair looks at fine cracks with crushing, surface spalling, crushing of concrete, breaking of ties. All of these require adequate level of intervention and post-repair enhanced performance. Similar things are shown to you of how concrete spalling, exposure of the main reinforcement and rebar is there on the left side, which you are repairing through a proper cleaning process and then replacing with new concrete, and if necessary with a strengthened jacketing. So when you do this kind of thing, you have to also worry about whether shear will control subsequently. So strengthening in one direction should not make something else take over the overall scenario. Scenario must be the way you want it. Connection of old and new reinforcement is a challenge. So there are welding or wiring mechanisms that people use. Strengthening of beams, jackets on four sides where accessible, otherwise use jacketing. Joints, how they are, how U-jacketing is done where you anchor the ends. Post-repair analysis, trying to give you participation of the repaired and original damaged material, how things evolve. Expressions that can be used in design computation. I will skip some of this. Anchorage where new concrete is added on damaged concrete. You want to have these U-pins that help you connect the new and the old. This is something I showed you earlier too, joint strengthening with pre-stressed collar. So this is a confining the joint to strengthen. So joint strengthening could also be done with jacketing. Glued plates at joints, these are typically heavy. So therefore FRP is sometimes more attractive where lightweight to high strength is possible. Strengthening of a wall with a jacket, strengthening of the slabs, local repair through slab thickness, you grout, increase thickness of the slab, connection of slab between connection details of old and new through connecting pins, end column jacketing, anchorage of column and jacketing, and finally footing repair. So all of these are concepts which need to be clearly understood, and thereafter repair needs to be introduced. I also take you through a little bit of bridge related intervention here in the successive slides. Span length should be short or long. Alternate pathways can be introduced. Abutment should be at right angles. So you can see, for example, in the top, there are uneven lengths. So by introducing a sleeve, you are making all columns of an equal length so that the stiffness gets distributed the same level to all columns. Otherwise, shorter columns will attract more force. Curved alignments can be problematic, and therefore it is important to understand how movements in curved alignments can be permitted to reduce the forces. Again, branching of roadways and junction can be critical in some of the seismic related design. So you introduce some kind of expansion joints there to allow for movement. And then here you are looking at something connected with footings, something different kinds of slabs, different kinds of connections between at the joints where you can grout and provide for continuity. Continuity can reduce the demand on the member. So that is a kind of intervention that is sometimes used. It can also shift the period and therefore reduce the force. So this is showing you how piers behave, and damage in the pier at the base needs to be improved so as to provide by way of intervention. These are some of the other kinds of sections that could be damaged and have different kinds of repair mechanisms that could be introduced. For example, a intermediate level cross beam can reduce the demand on the long pier columns by reducing the force. Similar things in terms of detailing, confining of the cross section, improving the footing connections through linked elements. All of these can enhance your overall repairability or performance. Similar things are also shown for foundations, choice of structures in deep valleys. All of these are suggestions rather, so that you have an idea of how to go about designing or intervening. Modeling concepts, how finite elements can be used in studying bridge models, how inertial masses, stiffness quantities are estimated, analysis could be done, and thereafter improved redistribution, etc. could be understood. So here you can see, for example, the differences in hysteretic energy absorption. The curve F knee joint is the most dissipative, B and E. The other ones are less dissipative because of the hinging action. This is trying to illustrate to you how you could possibly look at analysis of such systems. You could look at stiffness and mass matrix, having an understanding of modal response combinations, choice of elements for analysis, moving forward, how foundations are modeled, connections are modeled, and now I show you an example of pushover analysis. See, gravity alone has load versus moment versus curvature at yield and ductility. Inclusion of compressive loads on members will increase the ductility marginally, and will reduce the and will also increase the moment at yielding and moment at collapse. Whereas if you look at tensile axial loads, you are seeing a corresponding reduction in the yield and curvature moments. So reduction in moment capacity if you have tensile loads, enhancement in moment capacity if you have confining loads. So this is an illustration of a frame with two hinges at the base, real hinges, and continuity at the top, and you have progressively two hinge developments, and associated with it lateral displacements that occur, and associated with that you are trying to identify for a given seismic force what is the target displacement that can take place. So you are seeing, for example, the first analysis, which is elastic, looking at moments and associated seismic force. Change in column after the first hinge forms. That means after that, moment capacity at that joint will not increase, it will simply redistribute the additional load to other elements so that other points become hinges. So this progressive process of hinge formation needs to be enabled in your design. Redistribution is a good thing, and associated with that you have enhanced lateral movement, which needs to be computed and is accordingly shown here. An alternate thing that is often used is a substitute structure. Supposing I have damage, I am trying to arrive at post repair, looking at the structure as a elastic system post repair, and this system will lead to an evaluation of the repaired system assuming equivalent elasticity, wherein you are interested in arriving at effective stiffness and effective damping through such charts that people have created using modeling concepts that have been well documented. So using that, one can arrive at a suitable acceleration or displacement response spectra. I won't get into these details as Professor Raghu Prasad will be talking about it, but clearly damping will reduce the demand, and the idea of having a good idea of what is the level of damping that is actually available to you is a way forward in the process. So you have both acceleration and displacement response spectra that can be plotted, and associated with that you can arrive at your design criteria that addresses the target seismic force through suitable designing. So a substitute structure can be a way forward to arrive at the target force that you are accommodating with a given detailing. So I will skip these steps and just move forward to quickly illustrate some of these issues. And so seismic performance of different bridge configurations, multiply simply connected systems, multiply simply connected spans, all of these are possibilities by way of repair. Adding elements to reduce forces is the way forward. So I will quickly go through this. We are, I guess, approaching the closure. So let me quickly point out longitudinal fixing to between piers at different heights is a way of reducing the loads on members, just the same way as in the transverse direction linking columns at intermediate heights can be done. So you have procedures for seismic assessment, which look again at generic indicators, detailed analysis, seismicity, vulnerability, and based on the importance of the crossing, arriving at the level of serviceability limit state, damage control limit state, survivability limit state, associated capacity demand ratio analysis, through which you arrive at the required ductility, the provision for it, and the investment you are putting in to improve its performance. So some basic flaws exist in these studies. While displacement ductility can be related to force reduction, this cannot be extended to individual members, as relationship between member and structural ductility demands depend on structural geometry. So the backward and forward integration can lead to some misconceptions, and one needs to be careful. Effect of axial force, I pointed out earlier, is an important factor in this and must be carried forward. Pushover analysis is a static tool that one can use in first level understanding of seismic analysis, and can lead you to an effective analysis process. I will skip some of these and move forward. Assessment of member strength and deformation characteristics. Members' material strength needs to be assessed. Modified capacity design considerations must be used. Inelastic deformation mechanisms that develop could happen with shear, with flexure. You prefer ductile modes which are flexure driven. You don't want shear taking control of the situation. So residual capacity needs to be assessed before you provide intervention, and the nature of intervention should be one that is going in the path that you desire. So I will skip some of these. They are basically a reiteration of what we looked at in the context of buildings, but here in the context of bridges. So deformation capacity of hinges is an issue. You want lots of rotational capacity without an actual breakage, so that other sections can take on the enhanced load. So I will skip some of this. Yeah, now I come to some illustrative ways of showing link beam. In the case of a column pier, you are putting linkages at intermediate heights to improve or reduce the seismic forces. Similar things can also be done longitudinally. Here I am showing you how cap or pier cover can be repaired or retrofitted. Continuity is a way of reducing load. So linkages at the pier to make the beam continuous is a way of reducing the force or demand. So there are different ways in which you can provide intervention. This is a foundation repair. So now I will go into a little bit of repair per se. You could have FRP repair, you could have steel repair. FRP repair is a lighter, stronger way, but you again want a desired failure mode, delamination or rupture. How repair is done using jacketing. you are actually applying epoxy coating and fixing. There are different standards that are available to you for this kind of repair. As opposed to FRP repair, you can also have self-compacting concrete with fibers as a repair material, wherein you have to qualify your mix to be self-compacting. These are the L-box, pipe, J-ring are all methods by which you qualify your element. And these curves here show you how plateaus, long plateaus are highly ductile responses which are arrived in the repair material. So these are all ways by which you can enhance the repair. This is an illustration of a beam being repaired when it is flexure critical or shear critical. You can see that the overall performance improves. Flexure critical continues to remain flexure based in following repair, whereas shear critical, you are changing the mode to a flexure failure by enhancing the shear flexural capacity. So with this kind of repair, you are also increasing the ductility and you are allowing the primary structure to perform adequately. So it is also possible for you to analyze it in companion with the test with a proper modeling. You can introduce elements that look at concrete, look at steel, look at bond slip. All of these can be adequately captured in the model to give you the kind of overall target performance and reconciliation between expectation and what you are likely to provide. I will skip the analysis. The analysis is again like stress block based. You are accounting for the new material, its capacity, how by intervention you are still having a flexural ductile failure. Okay, I will skip through this. This is again a case of repair using SCC. You can see the kind of localized failure that takes place, but at a much higher gradual ductile mode. So here I am doing external reinforcement and jacketing. So that means the internal reinforcement is damaged and you are therefore having to put additional reinforcement and then providing the SCC on it. And you will see in this particular slide that there is a redistribution of forces through the primary bars and the additional bars that have been added in the external areas and are therefore properly linked to the primary element. So this is like bypass surgery. Now here I am showing you a case of arch bridge that was repaired in Bangalore some years back. It's an old masonry arch which was a defunct bridge. So one of the things that we had to do first was a load test to see that it had adequate ductility capacity. That means it's rebound when the load was removed. Following that, once we had a clarity that it had adequate ductility, we felt that it could be intervened into, and based on an analysis and model to provide for enhancement, we arrived at an improved repair system for this structure and thereby provided an economical solution of repairing a defunct bridge. So I will stop my presentation. I think this is the last slide. Repair and rehabilitation can result in considerable cost saving and restoration to original or enhanced strength if it is properly engineered. Thank you very much. I now end my presentation. If you have questions, I will be happy to respond to them.
Thank you, sir. Thank you for the very nice presentation.
Rather long, right? Be frank.
Sir. No, sir.
Okay.
So there are a few questions from the participants.
Go ahead.
One of the participant who has asked how to calculate strength index.
See, strength index is again it's an analysis process. You are looking at what is the target strength, what is the residual strength, and the difference between them vis-a-vis the target strength is a measure of the strength index. Now, when you retrofit it, you are going to higher values, then naturally the target value has to be, the margin has to be substantially higher in order to accomplish that.
Okay. Thank you, sir.
So you know a priori what is the original design and what its current capacity is. The loss or the reduction is the amount that you are making up in order to repair it. When you want to enhance it, you are retrofitting it.
Okay. That was one question which has been posed by one of the participants. I also would also request the participants, if any questions are there, kindly please post it.
Okay, no questions.
I see that many questions have come up.
Okay,
So
ask.
I would, since there are no questions at the moment, sir, we would like to conclude the session. It
Okay.
was a very informative session, sir. Thank you very much.
I will stop sharing.
Yeah, I thank you very much. We thank the Department of Civil Engineering, Ramaiah Institute of Technology. Thank you for your valuable time and to have shared your expertise and knowledge through this.
Thank you. I thank you for giving me this opportunity, and people are free to contact me through my email, which I have provided. I can be reached through email, and if there are questions, we can talk about it. I truly hope that people have understood it. I know that a large amount of material has been presented in a short duration, so there is only so much of capacity of absorption, but I truly hope that there is an adequate level of knowledge transfer that can enable this process. Thank you.
Thank you, sir.
Okay, so I will sign off.
Yes, sir.
Okay,
thank you, sir.
Thank you, one and all.
Thank you, sir. I would like to inform all the participants to kindly please be there. The feedback form is going to be shared. Please kindly share your feedback for the session. The next session is going to start by 2 o'clock, session 2 by Dr. Guru Prasad. And request all the participants to kindly log in 10 minutes earlier to the starting of the session. The session is going to be from 2 to 3:30. Using the same link, please. The same link which all of you all have used to join for the session, the same link is to be used for the forthcoming sessions for today as well as for all the other next 2 days too.